Today I'm going to cover chapter 16 thermochemistry, and this is about the calorimeter. First of all, let me explain to you guys the basic ideas of endothermic and exothermic reactions. So thermochemistry is all about the transfer of heat energy, how whether heat energy enters the system or leaves the system, and we have a specific name for those. So let's go ahead and take a look at this graph. So the y-axis for the energy and the x-axis for reaction coordinate. So the reaction starts from the left and ends on the right. So let's just say that a certain reaction, the energy of the reactant is down here, and then a final energy of the product is right here. If the energy level increases after the reaction is over, that's called endothermic. That's because energy has to enter the system to end up with a higher energy. And then whatever the energy, the little bump you must have in the process of the reaction is called activation energy. Exothermic looks different because exothermic means the exo means exiting, right? Then you have a higher energy in the reactant compared to the product. So in other words, after the reaction is over, the energy is going to leave the system and then becomes a lower amount of energy. Okay, and also a little bump that's required to perform the reaction is called activation energy. Okay, so what does it mean to have a temperature of 0 Celsius? You need to first understand what is temperature. Is temperature the same thing as heat? Well, the temperature is a measure of how hot or cold something is. Okay, so temperature and heat are not the same thing. Temperature is measured in arbitrary units such as Fahrenheit or Celsius. Temperature is directly proportional to the average kinetic energy of the molecules of the substance. Okay, so well, if particles, especially the gas particles, are under higher temperature, they're going to possess more average kinetic energy. So the temperature and kinetic energy are directly proportional. Okay, this sounds very familiar to us because we learned this already back in kinetic molecular theory, which was a fifth postulate. And then we know that kinetic energy, Ke, is equivalent to 1/2 mv square, m for the mass and v for the velocity. Okay, so the v is for the velocity or the speed, and temperature is therefore proportional to the speed of the molecules of a substance. Okay, the particles are going to move faster and faster as temperature increases. So the temperature and velocities are also directly proportional. Okay, this is a symbol for directly proportional. All right, so the higher the temperature, the greater the average speed of the molecules. Okay, now heat is the thermal energy that transferred from a hot object to a cold object. Remember, thermal energy or heat is always transferred from a higher temperature or the hotter object to the colder object. Heat is measured in energy units, joules or calories. So heat and temperature are two different things. Temperature is measured in Celsius or Kelvin or Fahrenheit, while the heat is actually measured in energy unit called joules or sometimes calories. The heat transferred is proportional to the mass of the object, the specific heat capacity, and also the temperature change. So the heat energy can be calculated by these three variables, okay? And we can actually put them mathematically put together. Heat has a symbol Q, and remember it's a lowercase q, and it's calculated using this formula. Q is equal to mc delta T, okay? In short, I usually call this one MCAT, I know the delta doesn't sound like A, but it kind of looks like A, so I just make it called MCAT. Okay, easy to memorize. Okay, so Q is for the quantity of a heat energy, M is for the mass, C is for the specific heat capacity, and T is for the temperature. Now, this triangle is actually called delta, and delta basically means the change. Okay, change of a temperature, meaning you will have to subtract the final temperature to the initial temperature. Okay, ending temperature to beginning temperature, and you look for the difference. That's called the delta T. Okay, specific heat capacity is the concept that's totally new to you guys. Okay, this is basically a unique the value for every matter. Okay, every matter has their own way of holding the heat energy before changing their temperature. For example, the specific heat capacity of water is known as a 4.18 joule per gram per Celsius. Okay, in other words, the water will require 4.18 joule, okay, in order to change the temperature of 1 Celsius of temperature of 1 gram. So this is basically a list of the unique specific heat capacity for many different matter. Okay, you do not have to memorize this because I'm going to give this to you. I'm going to give you guys a specific capacity unless I ask you to calculate one. So you do not need to memorize it. I just want you to know that, again, every matter has a different specific capacity. All right, the first law of thermodynamics. Energy cannot be created nor destroyed. That means only can be transferred between a system and the surroundings. The energy in the universe, therefore, is constant, and that means the energy has to be conserved. Okay, you just can't create or destroy energy. All right, to put it mathematically. All right, so whenever there's an energy transfer from one system to another system, for example, one object is hot, the other one is cold, so the heat energy moves from hot object to cold object. Okay, so the hot object is going to lose the heat energy while the cold object is going to gain the heat energy. Okay, so I'm going to call that the Q lost. Loss is for the subscript. So the hot object losing on heat energy and giving it to the colder object. Okay, the energy gained. Okay, these two are going to be has to be equal to each other. Okay, ideally, right? When energy transfer is perfect and ideal, that means amount of heat energy lost by the one system is the equal to the other one, but we're gonna have to put a negative sign in one of them, okay, to cancel those losing and gaining. All right, heat lost by the system is equivalent to the heat gained by the surrounding. And since the Q is equal to MCAT, that means the mass of the system, okay, or the system that's losing the energy, specific heat capacity of the system, multiplied by the change of temperature of the system is equivalent to the surrounding that's gaining the heat energy, the mass of the surrounding, specific heat capacity of the surrounding, and also the change of temperature of the surrounding must be equivalent to each other. Calorimetry is basically is a lab procedure to actually transfer the heat energy from one system to the other and then do the calculation. The amount of heat absorbed or released during a physical or chemical change can be measured, usually by the change in temperature of a known quantity of water. And 1 calorie is the heat required to raise the temperature of 1 gram of water by 1 Celsius. We also have a different unit system called a BTU. This is the heat required to raise the temperature of 1 pound of water by 1 Fahrenheit. The unit of heat used to modern thermochemistry is called joules. Joule. And joule is equivalent to 1 Newton times meter. And now this is a physics. You are going to learn about the Newton as a unit for the physics class, which is equivalent to 1 kilogram times a meter square over second square. And 4.184 joules is equivalent to 1 calorie. And calorie is the energy unit we use for the typically for food. And this is an sample bomb calorimeter, and this is what we use to calculate how much energy transfer from one system to the other. We actually use this cheap calorimeter as a lab, but we unfortunately can't be doing right now. But this is typically what's done for the calorimetry lab. So basically, what happens is that we have a styrofoam cup, and then we place the known quantity of water at a certain temperature, and when we heat up another object to the really high temperature, and we put it into the calorimeter, and then what happens is the water is going to cool down the object, and eventually the temperature is going to be reached somewhere in the middle, right? Because the hot object will transfer the heat energy to the water. When the temperature becomes the same, right? The energy transfer stops, and then we measure the final temperature, and we find out how much heat energy is transferred from one system to the other system. Due to the length of the video, I am going to post another video to do the sample practice problems.